Good evening. Welcome to ECE 442-542. This is a review session for exam number 1. I'm not going to spend a lot of time on the process. We've already talked about that in the class. It should be a copy of what we just talked about a few minutes ago. What you can and can't have. The main thing is that you can bring one sheet of notes. They don't have to be handwritten. You can have your own Z-transform table. It doesn't have to be the one from D2L, but that's the generic one that you can work from. In terms of material, we didn't talk about this a few minutes ago, I don't believe, but the topics, there's a list of topics, that's on D2L. Right below that, I believe I've now recently included reading material for this first exam, and it's based on the textbook that you can access through the library. You don't have to go buy one. I don't know if you could even find one now to get it here. Maybe you could if you have Amazon Prime. But hopefully you already have that if you need it. There are practice exams, and here I would say on these, pay attention. Pay attention to specific problems that are called out on older exams. The exam from spring of 14 is pretty consistent with the topics that we've covered in the spring of 15 for exam 1. Prior to that, it's not. And so I've had to pick and choose different topics from different exams, or pick and choose problems and where they're located on particular old exams, and that's why you need to pay particular attention to which exam is which. The material for exam number 1 will be on homeworks number 1 and 2, and all of the material up through last Wednesday's lecture. I hope that's the 4th of February. The previous lecture that we just had tonight isn't going to be, we won't be talking about region of convergence and bounded, but you do need to do Z-transforms on the exam. Here are some ideas and concepts that I will scroll through, and then we'll start working some problems, I hope. But you need to be able to do this dance. I call this the square dance, because it's in a square, but you need to be able to start with a differential equation and go to a block diagram, or start with a differential. Which semester am I in? This is difference, this is discrete, so this is a difference equation. These are discrete time systems. Start with a difference equation, Z-transform to obtain the transfer function. Or if you have a transfer function, you should be able to cross-multiply and inverse Z-transform. That one you will have to be able to inverse Z-transform, which really just means Z to the minus 1s and Z to the minus 2s. What do those correspond to in the time domain? X to the n minus 1 or X to the n minus 2. Those are delays, aren't they? That kind of inverse Z-transform you need to be able to do for exam 1. That's what I'm meaning by that script Z to the minus 1. You should be able to go from a transfer function to a difference equation. That's the left side of this square dance. The right side, you should be able to take a difference equation and produce a block diagram. That block diagram is in the time domain usually if you're starting in the time domain with a difference equation, and that means you're going to have delay blocks, an all delay block diagram. The key to going to the next point in that dance to get a state space representation is simply to label the outputs of those delay blocks as state variables. However many delay blocks you have will determine the big or the size of your state space representation. If you had 4 delay blocks, now you have 4 states. And each of those states are outputs of those delay blocks. Going into those delay blocks are now one advanced in time of each of those state variables. Meaning, let's say you labeled the rightmost delay block as x sub 1 at time n, little x sub 1 at n. Then the input to that delay block would be little x sub 1 at time n plus 1. And now those are what you're using, or you need to write those to create your state space representation. And we've defined those four matrices. Our system matrix is capital Phi, our input matrix is capital Gamma, our output matrix is H, and our direct feed-through matrix is J in a state space representation. And I was getting lazy or more concise. I was just subscripting with the time index. I wasn't saying here's the argument at time n. I just said x of n. And x could be a vector. Ooh, so maybe it is weird what I'm doing here, but I hope you understand what I'm trying to say. The subscript here is not the component in the state vector, it's the time index. Maybe I shouldn't have done that. I'm getting a little sloppy, but I hope it's clear what I'm meaning by that. Because little x is a tall, thin vector, and it could be, depending on how many delay blocks, if you had 4 delay blocks, x as a vector is 4 components tall. And you have x sub 1 of n, x sub 2 of n, x sub 3 of n, x sub 4 of n. All of those are contained in this vector right there. I hope that's clear. Then we will, if we haven't already, we will tonight hopefully show that you can go from the state space representation to a transfer function by this algebra, matrix algebra. The output matrix H times this matrix Zi, I is the identity matrix that's the same dimensionally as the system matrix Phi. So if you had a 4 by 4 Phi matrix, I is a 4 by 4 identity matrix. One's on the diagonal. You're now scaling each of those by this complex variable Z. You perform the matrix inverse of that 4 by 4 matrix, and on the exam you'll only have to compute maybe a 10 by 10 matrix symbolically invert that 10 by 10. That's probably all y'all have you do. And then you post-multiply that by the input matrix gamma, and then you add, if you have a non-zero direct feed-through matrix J, you would add that to that. We'll derive that formula, I hope, in a little bit. And that brings you back to a transfer function, g of s, that you could take into a difference equation. Do you see how you can dance around those 4 points on that square? That square dance you need to be very comfortable with, going around that square. Yes? So I have only indicated one direction on some of those progressions from corner to corner, for example, because that's sort of the way that we've talked about the way of progressing from a block diagram to state space. We really haven't talked about a state space to a block diagram, but I would say you should be able to very quickly do that. So we could, but I've drawn these arrows in the direction that we've done in class, or in this class so far. But you should be able to very easily go vertically up from state space to the block diagram, because you already have x at time n plus 1, and you could quickly draw, however, how many delay blocks would you need if you had a 3 by 3 Phi matrix? 3 delay blocks, and you now know what the outputs of those delay blocks are, x sub 1, x sub 2, and x sub 3. You could vertically stack those up and then have all sorts of interconnections depending on how interconnected your phi matrix is. But each entry in that phi tells you how you are connecting the different components of your state. And so it's actually sort of nice if you have this intuitive feel for block diagrams and state space. You can sort of feel how your system is interconnected, and you can think of it in terms of a block diagram, even though it's given to you as a state space representation. But some of these, going from a transfer function to a state space, that's not as immediate, but you could chase your tail and get there by going a little bit further around in this block diagram. If you could now go to a difference equation, go to a block diagram, and now you've got a state space if somebody gave you a transfer function. And that's the reason why I've put some of these arrows in just one direction. That's one little piece of what you need to be doing. You have the first 7 chapters of Sham's outline. Not all of those 7 chapters, but yesterday I was going, well, what have we covered? And so I started looking. I go, okay, we're doing a little bit better than what I maybe thought. Solution to difference equations. You should be able to do all of these. A homogeneous equation. That's when you have a zero forcing function and you just have initial conditions. What's the time domain solution? Non-homogeneous. Now you put in the forced with initial conditions and create this expression for a non-homogeneous equation. And the structure of y of n, what does that look like? Maybe you don't have to find the coefficients, alpha 1, alpha 2, but now, depending on what your modes are or where your poles are and the structure of your particular solution, that now gives you the structure of little y of n, and we'll try to cover that a little bit later. We're putting a lot on our plate, aren't we, that we're going to cover tonight. But you've probably all brought a sacked lunch. Ooh, I was going to say, and there's no wall clock, but this clock might be fairly accurate. It's a digital. Very appropriate. We're in a digital control class. So we'll talk about how you could find the structure of y of n for a forced or unforced. I hope this comes as no surprise to you as far as picking a sample period or a sampling frequency. The sampling frequency in radians per second is 30 times the closed loop bandwidth. And this is how you could relate that sampling frequency in radians per second to a sampling frequency in hertz or to the sample period capital T. That you should be comfortable with. Bounded output stability. Usually this implies that we're dealing with a causal input. And so all of these things you learned earlier tonight with anti-causal and causal and region of convergence and where your poles are might have confused you for the exam 1. If you want a stable system, where are your poles? I thought I wrote it down. They have to be in the unit circle. Okay? Your poles of your system are interior to the unit circle. They're not on the unit circle, because if you had a pole or poles on the unit circle, I could find a bounded input that would produce an unbounded output. You could just have a system that was as simple as a pole at 1, and I could give you a unit step in discrete time, and that would give you a ramp output in the time domain. Meaning your poles need to be inside. If I give you a question on the exam and I say, is this system, or is this difference equation, or is this block diagram, bounded input, bounded output stable, then you have to go from a difference equation to finding the poles or the roots of the characteristic equation. And then you'll find those, and you'll only hopefully need to factor a quadratic. So on your notes, write down the quadratic formula if you don't have that memorized. But those then need to have a magnitude. If they could be complex, but the magnitude of those poles need to be less than 1. Is that clear? And I could give you a system in many different forms. That's going back to the square dance. I could give it to you as a state space representation. I could give it to you as a difference equation. I could give it to you as a block diagram. I could give it to you as a transfer function. That would be a gift, wouldn't it? Then you just have to find the poles of that transfer function if it was one transfer function. Maybe I'll give you a few transfer functions and they'll be interconnected. You'll have to find the closed loop transfer function. Hint, hint. Okay? Equations of motion, we may not spend a lot of time on that, but I want you to come away with this unit or units, exam number 1 material, feeling comfortable with equations of motion, G of S's. A circuit, that will give you a G of S. A mechanical system, that will give you a G of S. Because we're going to be playing with these G of S's and converting those into discrete time system representations, subsequent to exam number 1. But we need to start somewhere, and that's where we started in homework 1. Z transforms. If I give you a waveform as a function of n in the time domain, can you compute the Z transform? That's why you have that Z transform table. Can you match up these time domain expressions with the transform? And you might have to use some Z transform operations to get it to look like what is in the table. I might give you a difference equation and ask you to find a transfer function. You have to Z transform the difference equation, which really means these delays convert into Z to the minus 1, Z to the minus 2, etc. That's fair, I think, trivial, right? To go from a difference equation to a transfer function. Block diagram. That one's even easier. If I give you a block diagram in the time domain, what do? You erase those D's or delays and replace them with Z to the minus 1 to get into the frequency domain. If I said, give me the give me the Z domain block diagram, if I gave you the gift of an all delay block diagram. Right? I probably wouldn't erase anything. I would resketch it exactly as it is, except I would now, instead of the delay, I would put Z to the minus 1. The gains and the summing junctions are all in the same place. Is that clear? I might ask you to find a transfer function. That might involve block diagram algebra, chapter 7 of Shams. It might involve Z transforming a difference equation. It might mean that you have to do some matrix algebra. And again, only a 10 by 10 matrix inverse symbolically for Wednesday. Pardon? Yes, if you have a certain calculator, your calculator can do that. Yes. Mason's gain does work for the z domain. So now if you have z to the minus 1s floating around, or subsystems, you maybe have a g sub 1 of z and a g sub 2 of z and an h of z, you could use Mason's gain to find that. You just are now working with the z domain. But we're not assuming that, so block diagram algebra works. But if you've had a previous controls class or a previous signals and systems class that talked about Mason's gain, you can use it. You just have to do it properly, in quotes. Yeah, you need to remember how to do it, but it can be used. But you don't have to have that for this material. Settling time. Earlier tonight we talked about the dominant mode of a system. What if I gave you a transfer function that had 3 poles, and I said, what's the settling time? What's the first assumption I'm making if I'm talking about settling time of a system? And if I'm talking about settling time, I'm now just really thinking about initial condition response. I'm not worrying about exciting that. I could excite it with a constant input, and it would then have the same length of time to reach a steady state. But let's just deal with initial condition responses. If I say settling time response, what am I implicitly assuming? Or not implicit, what am I assuming? That it's stable, isn't it? I'm at least assuming that the system is stable. So all of my poles are inside the unit circle. Now if I'm looking for settling time, which pole do I focus on? The dominant pole. Now what if I gave you complex poles? Which poles dominate? Suppose I gave you complex poles, they occur in conjugate pairs, don't they? Does it matter if they're on the right side or the left side of the imaginary axis? And now I'm assuming, if we're dealing with a stable response, that all of these are inside the unit circle. That's a given. But now which one or ones are dominant? You look to see the one that's the furthest away from the origin. You find the radius, you find the magnitude, you find the modulus, however you want to think about the length or the distance from those poles to the origin. It's just Pythagorean theorem. Real part squared plus the imaginary part squared, square rooted. You just finding the hypotenuse. You find the biggest hypotenuse. We're assuming it's less than 1, but that would be your dominating set of poles. In this case, if I'm seeing properly, those would be the dominating poles. And you would then compute that distance, that hypotenuse. Real part squared plus imaginary part squared, square rooted. Then you use, throw me the ball. I'm sorry, you can't tell what I'm talking. Sorry, we're in a room that reminds me of a court. So I'm running around on this court. But where was I? It's late, okay? Bear with me. It's time for a game. We have to do something. That R, that radius, is what you would put in that expression to find the settling time. Is that clear? And that r could be related to the imaginary part and the real part of those poles. If this was a distance a and this was a distance jb, then r is square root of a squared plus b squared. Is that clear? And then you could use your algebra to find what is capital N. If I'm asking for, let's say, the 1% settling time, then you want y of capital N to be 0.01 y of 0, and you solve that for capital N, assuming you've now determined capital R. Is that clear? Settling time determination? Oh, good. Now we can start playing. Okay? Find a state space representation for the following difference equation. What if I gave you a difference equation that's y of n equaling 1.4 y of n minus 1 minus 0.45 y of n minus 2 plus u of n minus 1 plus u of n minus 2. And that probably already is starting to make you nervous. Why? Not y of n, I'm sorry. WHY, question mark. Why might that make you nervous? Pardon? I'm thinking these delays in our input, right? In class, we talked about not having a delay in our input. Now we have them, and on a homework problem, which seemed to cause problems, I gave you delays in your input. You now had a non-unity numerator in your transfer function. That's what this represents. I'm going to go over a different way to find a state space representation from this. You can look at the solutions for the homework. Maybe I included this already, but the other way is what I tried to explain in words in the homework problem 3 on, problem 3 on homework number 2. Here, let me just say that here is a slightly different way of coming up with a state space representation. I will just say one construction approach. Meaning if you looked at this in the solutions and you go, I have no clue where he came up with this, this is going to hopefully help that process. The first thing that we are going to do is we will assume that we have access to the output at time n and the input at time n. And that's what I'm meaning by, let's assume that these two signals are available. Then what I'm going to do is I'm going to start collecting terms that have the same number of delays. I have an output and an input that are delayed 1, and I have an input and an output that are delayed by 2. Meaning I can create y of n. Unfortunately, that just slid off the top, but I can now say I have a delay, and now I'm looking for the two pieces that are delayed by 1 in time. If I process 1.4 y of n by 1 delay, I will have this first term. Is that clear? Meaning if I now write here, if I operate with a delay of 1.4 y of n, Is it clear that that's the same as that first term on the right-hand side? I've now, if I say y of n delayed 1, that's what this is. And u of n, I can also delay by 1. And so I've now accommodated those two yellow underlined terms on the right-hand side. Now I need to delay by 2 delays, so I'm now going to nest my delays. I haven't yet closed up that curly bracket. I'm going to introduce another bracket. I can't get very creative, so there's another bracket. Maybe I should have done that, but this red is inside the green. This delay, green delay, and the red delay are both operating on what's inside the red bracket. And one of the pieces inside the red bracket is going to be minus 0.45, and the other one is u of n minus 2. Meaning I can now, in here, say I have a minus 0.45 y of n, which will get delayed twice. Here's once, there's twice, to give me that term on the right. And I need to delay the input that clear? This red input u delayed once through the D, red D, twice through the green D. And that now, this right-hand side is the same expression as what I started with. Yes? So now the reason the question was, can you say d squared? I'm trying to do this so that I don't have to say d squared outside of anything. I actually want to build these up so that I now, in my block diagram, will have as an input what's coming out of this red collection. That's not explained very well, but hopefully in the block diagram you'll see what I'm meaning. Now what I'm saying first is that I want to have access to y of n and u of n. So I could say that I have a u of n here, and I have a y of n there. And y of n is actually coming right out of a delay block. So that what I'm doing now is I'm actually saying that this entire piece is now x1 of n, effectively. I'm going to label that delay block in a minute, but let me go ahead and say it there. So that the input to this delay block, is it clear that the input to the delay block is 1.4 y of n plus 1 times u of n? Let me put those in. I'm claiming that I have y of n available, so let me pull this off. And it's now 1.4 with a minus. And u of n is going into this delay block plus what's coming out of that red stuff. And that red stuff is coming out of another delay. And what's in red, or what's going into this delay block, is again a linear combination of y and u. So that this red block, maybe I should have color coded this more, but I now have minus 0.45. Whoops. Was there not a... You guys need to wake me up. I told you it was getting late. That was just a 1.4, no minus sign. Here I have a minus 0.45, and I have a 1 u of n. That feeds, or that's the input to this rightmost delay, and the output of that, which is right here, is what all of this is. So I have 1.4 y of n plus u of n plus star all going into this rightmost delay. And how do I label the outputs of my delay blocks? As state variables. Meaning this particular point is now x sub 1 of n plus 1, and this is x sub 2 of n plus 1. The nice things in this is that y of n is the same as x1 of n, and I can now quickly write down my state space representation. I can now write down that x sub 1 of n plus 1 and x sub 2 of n plus 1. Those are my vector on the left of my equality. I now need to say that's some linear combination of states plus some linear combination of the input. x1 of n plus 1 is 1.4 x1 of n. Is there anything else in the top row of that system matrix? Now I'm basically saying I'm trying to find what the output of that summing junction is equal to. That's this output. It has to equal what's coming into that summing junction. And I've already accounted for 1.4 x1 of n. Another term is x sub 2 of n. And I can pull that up by simply putting a 1 in that system matrix to pull off x sub 2 of n. And I also have the signal coming in vertically from the top, and that's just u of n. What is x sub 2 of n plus 1? I hope you see that it's minus 0.45 x sub 1. There's no x sub 2 of n feeding directly back into that summing junction, and there is a u of n. This is our system matrix. This is our input matrix. And our output matrix, if we needed a state space representation, I only had one output, which means that these matrices that are producing y of n need to be one row tall. What is making up y of n? Is u of n directly creating y of n? There's a summing junction, and it's not very explicitly shown there to create y of n. There is no direct connection between the input and the output. This is a 0. X sub 2 is not coming in directly. X sub 1 is with a 1 and a 0. This output matrix is the H. This is the J. And now you could answer is that system stable? And now do you see what we started with? We could have started with that difference equation. You could have z-transformed that and found the transfer function and looked at the poles of that transfer function to determine stability. Maybe I had you get a state space representation. Now you have a block diagram. You could answer that question if it's stable. You've labeled the outputs of the delay block. You've now come up with a state space representation. You could determine stability of this. If you're given this state space representation and I say, is this system stable? What are you looking for here? Do you remember? You're looking at the system matrix. The system matrix, capital Phi, determines stability. And you're looking at the eigenvalues of that Phi matrix and wanting to make sure they're inside the unit circle. Is the system stable? You could say, well, one way to determine that would be to find the eigenvalues of Phi. And there you could say, oh, that's the determinant of lambda I minus Phi equaling 0. In this case, it's lambda minus 1.4 minus 1.45 lambda minus 0. I think that was my my Phi matrix. You now have the product of the diagonals minus the product of the off diagonals. Wasn't that convenient? So that factored. And if you couldn't see that, you could apply the quadratic formula, and it better give you the same roots. You now have a pole at 0.9 and a pole at 1/2. Which one dominates? And when I say which one dominates, I'm really meaning which one tends to linger the longest in a transient response. Which one is the slowest acting? You have roots at 0.9, or values of lambda that cause that to vanish. They are now at 0.9 and 0.5. Oh, we needed to answer the stability question. Both of those have a magnitude less than 1, so your system is stable. And which root is dominant? Pardon? The one that's closest to the unit circle, isn't it? 0.9. And you could then use that lambda or that capital R to find your settling time, couldn't you? Settling time 1% would be this y of n, which you could say for 1% is 0.1 y of 0 is r to the n y of 0. R is now that 0.9, and you can solve that for capital N. And N would tell you the number of sample periods to get you within 1% of where you started. That was one way of assessing stability. Another way would be to, my favorite would probably be Z transform that difference equation, unless I was explicit. explicitly asked to find a state space representation. If nobody told me anything about a state space representation, I'd probably z-transform that difference equation, find the transfer function, or find the characteristic equation, find the poles, meaning you now can, from this, I hope, see that you now have capital Y of z is equal to z to the minus 1, 1.4 y of z, minus 0.45 z to the minus 2 y of z, plus z to the minus 1 u of z, plus z to the minus 2 u of z, or I now have 1 minus 1.4 z to the minus 1, plus 0.45 z to the minus 2, sometimes students get confused as far as the transfer function. They put u over y. No, it's y over u. That's the g of z. That's now this z to the minus 1 plus z to the minus 2 over 1 minus 1.4 z to the minus 1 plus and we could multiply both top and bottom by z squared, and we have z plus 1 over z squared minus 1.4z plus 0.45, and now we can look at the poles. Not sure my word stable is stable, but the system is stable. If you weren't watching real quick, you maybe didn't see that instability in my word stable. Are there questions on that? I promised we would get to going from a state space representation to a transfer function. We just derived the transfer function from the difference equation. We have a way of checking our answer now. What is the transfer function? Of the given state space representation. We have a state space representation that's x of n plus 1, capital phi x of n plus gamma u of n. Y of n is equal to h x of n plus j u of n. X again is a tall, thin vector. It could be 10 components tall if we had 10 state variables, 10 delay blocks. In this example, it was just 2, wasn't it? X was an x sub 1 and an x sub 2. If we z-transform this, phi, gamma, h, and j are constant matrices. We don't have to worry about the z-transform of those. Those slide right through. And we're saying that the z-transform of little x of n is capital X of z. The z transform of little u of n is capital U of z. And if we z transform the output equation, which is just a linear equation, no dynamics there, z is a scalar, and we want to combine the capital X of z terms, which means we'll go ahead and be able to do that if we inject this identity matrix, capital I, in between z and x. And we can now factor this, meaning we can take this and say we now have zi minus phi or we can solve for capital X of z by inverting that matrix zi minus phi. We now want to use this X of z there. And we then have a way of connecting the input with the output without any intermediate variables. We can now say that we have y of z is h times capital X of z, which is zi minus phi inverse gamma u of z. And we can't forget the j u of z plus j u of z. And if we factor everything or all the u's out onto the right, we have in curly braces h zi minus phi inverse gamma plus j where this is the transfer function that I said we were going to compute. Yes. Why did I put I there? Z is a scalar. That's a complex frequency variable. And Z times capital X is fine. Z is scaling each of those components in capital X. So we actually have capital X sub 1 of Z, capital X sub 2 of Z buried inside that capital X of Z. Over on the right-hand side of that equality sign, I have a phi matrix, a 2 by 2 times a 2 by 1 vector. I want to be able to factor out capital X of Z, and if I have a scalar, I can't add or subtract that with a 2 by 2 matrix phi. To make it compatible, I need to insert this identity matrix. It's the same thing if you just look at Z times a vector capital X or Z times the 2 by 2 identity times that same capital X. You get the same answer. It's now I'm able to add and subtract a 2 by 2 phi matrix with a scalar scaling an identity matrix. That's where the identity matrix came from. You should be able to simply write this on your notes and know how to compute it. In our case, if we did that with the matrices that we have available to us, we have H, which was 1, 0. We have Z minus phi. Z is on the diagonal because of the identity matrix, and we have Z minus the 1, 1 entry of phi. We have minus 1 in the 1, 2 entry. We had a minus 0.45 in Z, which we're subtracting in the 2, 1 entry. That now becomes a 0.45. And the 2, 2 entry of phi was blank. It was 0, and we're taking Z minus that entry in the 2, 2 location. We need to invert that, post-multiply by our input matrix gamma, and add to that the J matrix, which is a 1 by 1 matrix. And I may not go through the algebra, but you should be able to. The determinant of that is the product of the diagonal minus the product of the off diagonal, and then you have the nice result for a 2 by 2. You can interchange the diagonals and change the sign on the off diagonal, and that's your inverse when you divide by the determinant. But you'll end up with then the same answer that we had before. Or you let your calculator do it, I guess. In some cases, your calculator is up here, right? Between your ears. And we've already talked about the settling time, haven't we? What's it influenced by? If I gave you that transfer function and I said, what's the settling time of that system if it had to decay from an initial condition, what would you be doing? Pardon? You'd look at the poles, wouldn't you? You would factor that denominator. You now have poles at 0.9 and 0.5. Now I want to know what's the settling time. You have to find the slowest pole, don't you? And that's the one closest to the unit circle. That's the 0.9. And then, so in this case, you could say, oh, here is my system. I have a pole at 0.5 and I have another pole at 0.9. Here is the slow mode. And there's the fast mode. The slow mode is the magnitude of z is closest to 1.0. Or you might have heard me say this is now the dominant pole. Which was that problem again. And if you go through that, you should find that n is a little bit less than 44. It's 43.7, but you need to round up. You should find that it takes 44 samples to settle. Now, suppose that I said or asked the following question. See how much I can do with one difference equation? Remember this difference equation? Wow, wherever it was. There, 20 years ago. Here is our difference equation. What if I now applied a particular input to that, a particular u of n, and I said, what is y of n? What's the structure of y of n going to be? What's the solution going to look like structurally? Let me give you a y of n. If u of n is equal to 0.7 n cosine of pi over 8n for n greater than or equal to 0, what is the structure of y of n? I don't need to know the exact answer. You could find it given enough time. On the exam, you're not going to have enough time, but you should be able to write down rather quickly what the structure of y of n is if you have that difference equation that we introduced 20 years ago with this input. How do you find, or what's the process for finding the structure of y of n? What's the first thing you probably need to be thinking? The homogeneous solution. You need to know what naturally, if you went up and kicked that difference equation, how would it shake? What would be its natural behavior? And what influences its natural behavior is what happens in the homogeneous equation. First, we need to find the homogeneous structure, or the natural behavior of the system. Or the system, if you went and excited it, how would it naturally like to behave? Or if you provided some initial conditions, how would it naturally want to evolve in time? Can you tell me, based on what we've talked about, the homogeneous structure? I'll just call it y sub h of n. Given what we've already talked about tonight in this little review session, what is the homogeneous structure of y of n? What makes up this structure of y of n? So now you have the poles, you have the eigenvalues, it's the same thing. Those modes influence your natural behavior. You had two poles, didn't you? You have two modes. We'll talk maybe a little bit later if you had complex poles. If you had complex poles, you would have their radial distance and their angle that would influence their structure. Here, we had real poles. We had one pole at 0.5, so we could say, oh, scale that by an alpha 1, and that's 0.5 to the n. We had another pole at 0.9. We'll raise that to n and have that with an alpha 2, and that's what the structure of an initial condition response would look like based on that earlier difference equation. It has two modes at 1/2 and 0.9. We would have to find alpha 1 and alpha 2 in what way? If somebody asks you to find those. And if I say structure, I'm not asking you for alpha 1 and alpha 2. Those can be left as constants, unknown constants. But if given enough time, how would you find alpha 1 and alpha 2? Initial conditions. And that's assuming you didn't have an input. We actually have an input. Now we need to find the particular structure. And this is actually the response due to the signals that are forcing our system. So that could be a function or functions. What's the structure of the particular solution? Y sub p of n, given this input. Now what am I doing? I'm going up to this system and I'm shaking it. How am I shaking it? Based on that U. So my shaking is decaying, isn't it? Because I have an R that's less than 1, and that's getting collapsed, and I have a particular frequency, pi over 8. So do you see this exponentially decaying cosine waveform that's being applied to the system? what's going to happen in your system? What are you going to see if you force it with this kind of excitation? Is it too late? It's going to look like what you're using to shake it, isn't it? The particular solution, except now there may be some delay between the input and the output, and that delay really is represented by saying I have an exponentially damped cosine piece and I have an exponentially damped sine piece. I'm going to have both. And if you just want the structure, I'm not going to give you the coefficients. I'm just going to say you have a cosine exponentially damped and a sine exponentially damped, and I'm just going to give you coefficients. The particular solution structure here would then be beta 1, 0.7 n cosine pi over 8n plus beta 2, 0.7 n sine pi over 8n. And if I wanted the entire solution, the total solution, I would be combining those structures, the natural structure and the particular structure, so that I now have alpha 1 bar times 0.5 to the n plus alpha 2 bar. Notice that's not the same alpha that I had before, because there I was just looking at the homogeneous. Now I have a forced solution plus a beta 1 bar, 0.7 n cosine pi over 8n plus a beta 2 bar, 0.7 n sine pi over 8n. And I didn't tell you that you needed to find the alphas and the betas. Is that clear, though, where that came from? Yes. So the sine and the cosine, how can I explain that again? What if I said, well, let me try to explain it differently. Is it clear that I could combine that sine and cosine into a cosine with a phase shift? Maybe not, but take something like this. Suppose that you had a gamma 1, 0.7 n cosine pi over 8n plus phi. Now I could apply my cosine of the sum of two angles. I could say, oh, this is cosine pi over 8n cosine of phi minus sine pi over 8n sine of phi. And now do you see where that sine and cosine might come from? It comes from a delay between the input excitation and the output y. That delay is related to this phi, and that phi actually gives rise to a sine piece and a cosine piece. So all you have to know is if somebody starts shaking something with an exponentially damped sine, you generically are going to have the exponentially damped sine and the exponentially damped cosine. You may not know what fraction of each you have, but you're going to have a combination. That's what I'm saying. So that sine came into play because there's generically delay between the input and the output, u and y. And that delay can be thought of as a phi in the argument of the cosine. And if you look at the cosine of a plus b, that trigonometric identity, then I hope that you start to see where that sine term comes from. So you don't need to include the cosine phi and the sine phi because we are absorbing all of those into our coefficient. because the phi is a constant. Cosine of phi is just a number. And it will change the scaling on the cosine. The sine of phi will change the scaling on the sine. And is that okay? So that's where your both terms come into play. Now, how could I change it up a little bit? Here's one more kicker, and then we'll call it good. How's that? Oh, no kickers in this room. It's not high enough ceiling. But sorry. We were playing a different sport, weren't we? I guess we, no, never mind. What if I gave you a pole zero diagram and I ask you for the structure of the output associated with those poles and zeros? So given a pole zero diagram, let's say for capital X of Z, what is the structure of little x of n? What? I told you we'd have a kicker. This will kick us, but it's not going to kick us very hard. We're going to figure this out. What am I saying? Well, boy, I can't scroll, can I? That's why I'm wanting to kick. Better not kick this laptop. Sorry, I'm just talking to myself. Don't worry about. Suppose we have a pole at 0.75 plus j 0.25. Then we know we have its conjugate, because we are assuming we have real coefficients in our expression for capital X of Z. And suppose we have another pole at 0.5, and maybe we have a 0 at 0.25 and a 0 at the origin. Could you give me the transfer function for capital X of Z if I say don't worry about the gain, the numerator gain? I'll just give us a numerator gain of alpha. Can you write down the transfer function now for capital X of Z? Should be by inspection. You have a 0 at the origin. You have a 0 at 0.25, and it's in the right half plane. There's the z minus 0.25. Then you have a pole at 0.5. And now we have complex conjugate poles, but we could write that as z minus 0.75 squared plus 0.25 squared. And I'll let you go home and figure that one out. Now, what's the structure of little x of n? But this should be, if you set this square bracketed denominator term, this quadratic, equal to 0, you should see that the roots are real part 0.75 and imaginary parts 0.25. Convince yourself that that's true. You need to get comfortable with that. But we could also go back to this. This is written in rectangular form, but you could also write this in polar form, which a lot of times now that you are starting to learn discrete control or discrete time ideas, polar form might be more helpful. The polar form of this, you'll just have to believe me, is 0.7902 at an angle of, and you would maybe want that in radians, but I can think more clearly in angles, in degrees, so it's 18.43 degrees. We're a distance 0.79 from the origin at an angle of 18 degrees, 18.4 degrees. You could find that by just getting Pythagorean theorem and the inverse tangent with 0.75 and 0.25. Now, what's the structure of little x of n with this pole zero diagram? Is your response stable? What influences stability? Poles, zeros, an average of poles and zeros? Are we learning anything in this class? What do we concentrate on for stability? Poles. And what piece of the pole do we focus on for stability? We concentrate on the real part if our poles are real, but if they're complex, we need to worry about the magnitude, don't we? The modulus. Because we're worried about their distance from the origin and how far away can they be from the origin and they still be stable. They can't be having a magnitude of 1 or more, can they? Or then we will go unbounded, or we'll grow with time. Are these 3 poles stable? Yes. We have 2 poles with a magnitude of 0.79 and another one with a magnitude real of 0.5. Which ones dominate? Which pole or poles dominate our response? Did you guys hear that? It's the one that has the largest magnitude, isn't it? The complex poles. What's our structure of the little x of n? Can you tell me that now? If you went up and just kicked this system, I'm not exciting this system, it's already, everything is included, capital X of z is all there, and now I say it's initialized, let it go. And what are you going to see? What kind of a response are you going to see from capital X of z when you look at little x of n? You just told me it's stable, so everything is going to collapse, isn't it, as n increases. How is it collapsing? You've already told me maybe that the 0.5 is going to collapse quicker than the 0.79, because if you square 0.79, that's not as small as 0.5 squared, and you can cube them, 0.79 is dominating. What do you see with the 0.5 in the response? Is it clear that you would have something like this? That's part of the structure of little x of n. What else are you going to see? You're going to have more decay, aren't you? But it's decaying based on its radius or distance away from the origin, which I said was 0.7902. But it had, what happens if you, so now think of this as a complex number. It's 0.79 at an angle. You square that. What happens to the magnitude? It gets squared, 0.79 squared. It collapses. What happens to the angle when you square that complex number? It doubles, doesn't it? You're adding, so you're rotating around that, if you wanted to think of it this way. It's collapsing, and you're increasing the angle, which means that in terms of a time domain response, this is going to be a cosine, and here you probably should have it in radians, but as long as you use your calculator right, it's 18.43 degrees times n. Is that clear? But is that all there is? What did we talk about before with cosines and sines? We don't know exactly if it's going to be all cosine, do we? We could have some sine, or it could be a phase-shifted cosine, so you need to include the sine term. And you would say, oh, plus beta 2, 0.7902 to the n sine of 18.43 degrees n. And that's the structure of the response just due to a pole zero diagram. That pole zero diagram is very powerful. Is that clear? Do you see that that sine and cosine could be just combined into a cosine with a phase shift by using trig? You can write your trig teacher a thank you note tonight when you're studying. Dear Mrs. K, thank you so much for teaching me the trig identity, cosine of A plus B. Yes? That pole zero diagram is in the z-plane, which maybe I didn't label, but we are mostly focusing on discrete time systems, so most of our planes will be z, although I could have S-plane to Z-plane mapping, which I didn't put on this. It's there. It's in the list of topics, so I haven't covered everything, but what can you understand from the Z-plane to S-plane mapping? This should help you understand why we can relate different parts of the S-plane to the Z-plane. What part are we doing in particular? The imaginary axis in the S-plane maps to what in the Z-plane? The unit circle, doesn't it? Because there we have in the imaginary axis S is just j omega. And this mapping, so if we take it through there, we now have z is equal to e to the s. What's the magnitude of that complex number? Use Euler if you want. Cosine omega t plus j sine omega t. The magnitude of that is cosine squared omega t plus sine squared omega t. Dear Mrs. K, thank you so much for teaching me trigonometry and introducing me to Euler. Right? This should convince you that the imaginary axis in the S-plane does map into the unit circle in the Z-plane. And that's your stability boundary. Your stability boundary in the Z-plane is this unit circle, just like the imaginary axis is your stability boundary in the S-plane. We will use this a lot later when we start looking at second-order system response and where does that correspond to in the Z-plane. But for now, this is the main connection, but you should be able to take any S-plane point and map it into the Z-plane. Just using that relationship. And that we derived or connected because we said a unit delay, z to the minus 1, is like a delay of e to the minus st, right, in the S-plane. And that made our connection with S and Z. So the S-plane and the X and Y axis, we have the real part of S and the imaginary part, just like we use the same terminology in the Z-plane. But now, if you had a positive right half plane pole in the S-plane, what does that do in the Z-plane? Where does that map? If it was in the right half plane, so now let's say that we have here is our S-plane, and if I picked a pole over here, what do you know that pole is in the S-plane corresponding to? Is that a stable system or unstable? Let's say this is plus 2. Pardon? So that's unstable, isn't it? Now we have z is equal to e to the 2t. What's e to the 2t? No matter what capital T is, what is e to the 2t? Say t is 0.1. This is something bigger than 1 in magnitude, isn't it? It's outside the unit circle. So anything in the right half plane and the s-plane is going to be unstable in the time domain and the continuous time, and it will correspond to unstable in the z-plane. It's when you have poles in the left half plane, then you have negative exponents in the z-plane, and that will bring you inside the unit circle. You now have a magnitude less than 1. Think of what e to the x looks like as a function of x. And at e to the 0, what's that as a number? E to the 0. 2.7 something raised to the 0 is 1. So that's the transition. And if you go positive, then it's bigger than 1. If you go negative, it's less than 1. Is that okay? So thank Mrs. K. And we will see you Wednesday. I sure hope